Section: Introduction. In this section, we discuss the advancements in diffusion models, which have recently shown great promise in generating high-dimensional data such as images, videos, audio, text, and 3D objects. Beyond just generation, we note that these models have been effectively used to tackle inverse problems without needing fine-tuning. The aim here is to recover data from degraded measurements. We highlight that some approaches modify the inference process of diffusion models to ensure that the generated samples align with the measurements. Other methods involve variational inference, Bayesian filtering, and solving optimization problems during the sampling process. A key challenge we face is that the posterior distribution, which represents the relationship between the clean data and the measurements, is only defined for clean samples. However, during sampling, we need to estimate this posterior at each diffusion step. To address this, we utilize Tweedy's formula to approximate the posterior, which allows us to apply it to various inverse problems. Yet, we recognize that this approximation can be inaccurate, especially in high-noise situations, resulting in lower-quality samples. To improve this, we introduce the concept of pseudo-inverting the measurements and enhancing the diffusion model by adding extra guidance or resampling processes. Our main contribution is the introduction of the Diffusion Posterior MCMC, DPMC, algorithm, which employs annealed Markov chain Monte Carlo, MCMC, to refine the solution of inverse problems. MCMC is a powerful technique for sampling from complex distributions and is commonly used in training energy-based models and sampling from diffusion models. We propose using a sequence of posterior distributions derived from measurements to guide the MCMC process. We also note that previous works have applied annealed MCMC with Langevin dynamics to inverse problems, but these methods can struggle with noisy or nonlinear measurements. Instead of executing a single MCMC step at each noise level, we suggest constructing intermediate distributions based on our approximated posteriors and running multiple sampling steps at each noise level, which has shown to enhance performance. In summary, we present the DPMC algorithm, which outperforms existing methods in terms of sample quality across various inverse problems, including both linear and nonlinear cases. Our extensive studies demonstrate the effectiveness of MCMC-based approaches and show that increasing the number of sampling steps consistently improves performance. Section Summary. In this section, we discuss the advancements of diffusion models in high-dimensional data generation and their application to inverse problems, highlighting our proposed Diffusion Posterior MCMC, DPMC, algorithm, which improves sample quality by leveraging annealed MCMC to better approximate posterior distributions. We demonstrate that DPMC outperforms existing methods, including DPS, across various inverse problems, emphasizing the effectiveness of MCMC-based approaches in enhancing performance with increased sampling steps. Section: Diffusion Posterior Sampling. In this section, we discuss diffusion posterior sampling, DPS, to tackle the challenging inverse problem. We utilize pre-trained diffusion models as a prior and introduce an iterative optimization method. According to Bayes' rule, we can express the gradient of the posterior distribution in terms of two components, one derived from the diffusion model and the other from the measurement data. We estimate the first component using the pre-trained model. In our approach, we simplify the relationship between the noisy observation and the clean image, allowing us to estimate the clean image based on the noisy data. Next, we present our DPMC model, which merges diffusion models with Markov chain Monte Carlo, MCMC, sampling. The diffusion models help in progressively reducing noise, while MCMC provides guidance based on the measurements. We note that the accuracy of our approximation depends on the noise level. At low noise, our estimates can be quite accurate, but at high noise, they may become less reliable. To improve our results, we turn to MCMC sampling, which does not require knowledge of the distributions at each step, unlike diffusion models. We employ an annealed MCMC technique, where samples transition through a series of intermediate distributions with varying temperatures. This allows us to bridge the gap between different distributions effectively. We define these intermediate distributions and do not expect them to perfectly match the true posterior at every step. Instead, we only need them to align at the clean image distribution. Our approach involves a proposal stage, where we denoise samples to create a good starting point for the next distribution, and an exploration stage, where we refine these samples using MCMC updates. We call our algorithm Diffusion Posterior MCMC, DPMC, and provide a theoretical analysis showing that the conditional distribution produced by DPMC is close to the true distribution under certain conditions. For implementation, we introduce a step size that is inversely proportional to the optimization distance, which helps in achieving more stable results. We find that while MCMC may increase sampling time, DPMC allows us to reduce the number of intermediate distributions needed. We can skip early high noise stages and start MCMC sampling from moderate noise levels, while at low noise levels, we can directly use DPS. Ultimately, we observe that DPMC yields better results than DPS with fewer evaluations. Section Summary. In this section, we introduce diffusion posterior sampling, DPS, and our enhanced model, Diffusion Posterior MCMC, DPMC, which combines diffusion models for denoising with Markov chain Monte Carlo, MCMC, sampling for improved conditional guidance. We demonstrate that DPMC effectively bridges the gap between noisy observations and clean data distributions, achieving better results with fewer evaluations by strategically applying MCMC sampling at intermediate noise levels. Section: Experiments. In this section, we conduct experiments on our DPMC method, which shows better performance than existing methods in diffusion posterior sampling. We begin by detailing the models, datasets, and experimental settings. For our experiments, we use the FFHQ dataset and the ImageNet dataset, both sized at 256 by 256 pixels. We utilize 1,000 validation images from each dataset. For FFHQ, we employ a pretrained model, and similarly, we use a pretrained model for ImageNet. We assess the effectiveness of our DPMC algorithm on several inverse problems. I. Super resolution with 4 times bicubic downsampling. E. Random inpainting with both box and random masks. E. Deblurring using Gaussian and motion blur kernels. And IV. Phase retrieval, where we apply a Fourier transformation and only use the Fourier magnitude for measurements. The first 3 problems are linear, while the fourth is nonlinear. We introduce Gaussian noise with a standard deviation of 0.05 for all tasks and adjust parameters accordingly for fair comparisons. For hyperparameter settings, we use the DDIM sampler with a default variance of 0. We set 200 intermediate distributions and perform 4 MCMC steps at each distribution. We empirically determine that certain schedules work well across all settings. We apply the proposal exploration step during the middle 60% of the sampling process, while using the original DPS sampler for the first 30% and last 10%. However, for the inpainting task with a box mask on ImageNet, we find that extending the proposal exploration step until we achieve clean images yields better results. Overall, the number of function evaluations for this setting is around 700, which is less than the 1,000 evaluations required by DPS. All experiments are conducted on a single NVIDIA A100 GPU, and we provide the running time for DPMC in the appendix. For our baselines, we compare the DPMC algorithm against several methods on linear inverse problems, including the original DPS, filter posterior sampling with and without sequential Monte Carlo, denoising diffusion restoration models, manifold constrained gradients, plug-and-play alternating direction method of multipliers, score-based SDE, and total variation regularized optimization. For phase retrieval, we compare DPMC with DPS, oversampling smoothness, hybrid input-output, and error reduction algorithms. In our experimental results, we focus on linear inverse problems using the FFHQ and ImageNet datasets. We present qualitative samples for each task, demonstrating that DPMC can generate valid outputs from noisy inputs. Given the information loss during image degradation, restoring the original image is challenging. Instead, an effective algorithm should fill in meaningful content that aligns with the noisy observations, especially in tasks with significant information loss, like inpainting. We show examples where DPMC generates diverse samples from the same noisy input in the inpainting task. We report the LPIPS and FID scores, which measure the similarity of generated samples to the ground truth and the distribution differences between generated samples and observations, respectively. DPMC achieves comparable or superior results to DPS across all tasks while using fewer evaluations. Qualitative comparisons reveal that DPMC produces clearer samples with more detail than DPS. In our nonlinear inverse problem experiments, we focus on phase retrieval using the FFHQ dataset. We again use 200 intermediate distributions and 6 MCMC steps at each distribution, applying the proposal exploration step during the middle 60% of the sampling. We find that the quality of the final samples depends on the initialization, so we generate 4 samples and select the best one. Our results show that DPMC outperforms DPS in LPIPS while achieving a similar FID score.